Hello everyone. This is the fourth class on the mechanics of solids. In this class, we will study the uniform bending. This class is about uniform bending. What is meant by uniform bending? In uniform bending, the beam is loaded uniformly on its both ends. In uniform bending, the beam is loaded uniformly on its both ends, and as a result, the beam will bend, and the bent beam forms an arc of a circle. That is, the beam is loaded equally at equal distances from the knife edge as shown in figure, and as a result the beam will bend and the bent beam forms an arc of a circle. Therefore, the bending is uniform. Since the bent beam forms an arc of a circle with constant radius of curvature, therefore, the bending is said to be uniform. Now, due to this bending, there is an elevation at the middle point of the beam. There is an elevation at the middle point of the beam, and we have to find out the elevation at the middle point. Now, consider a beam of negligible mass which is supported symmetrically on two knife edges at A and B. Consider a beam which is supported symmetrically on two knife edges A and B. Let AB is equal to L. Let the length AB is equal to L. Let the length AB be L. Now, in uniform bending, equal weights W and W are suspended from the beam at point C and at point D, with AC is equal to P and BD is also equal to P. That is, in uniform bending, equal weights are suspended at equal distances from the knife edge. Now, what happens then? Because of this loading, the beam will bend and it forms an arc of a circle like this. Now, there is a reaction at A and reaction at B. The reaction at A and B will be W, and they are pointing vertically upwards. The reaction at A is W and the reaction at B is also W, and they act vertically upwards. We have to find out the elevation at the middle point of the beam. Due to this bending, there is an elevation at the midpoint. How much the midpoint deflects, that we have to find out. This is the schematic representation of uniform bending. As I specified, consider a beam of negligible mass which is supported symmetrically on two knife edges at A and B. The length AB is equal to L. Let the length AB be L. Equal weights, that is W, are suspended from the beam at point C and also at point D. Let AC is equal to P and BD, the length BD is equal to P. That is, here equal weights are loaded at equal distances from the knife edge, and as a result, the beam is bent into the form of an arc of a circle. The beam is bent into the form of an arc of a circle with constant radius of curvature. So this kind of bending is called uniform bending. The reaction at A is W. The reaction at B is also W, where W is equal to mg, which act vertically upwards. What is our aim? Our aim is to find out the elevation at the middle point E. E is the middle point of the beam. Due to uniform bending, the middle point undergo an elevation, and how much it is elevated before bending. That we have to find out. I am representing the elevation at the middle point by the letter delta. So our aim is to find out the elevation of the middle point E due to loading. As I specified, in uniform bending, the beam is bent into the form of an arc of a circle. Why it bent into the form of an arc of a circle? Because it is loaded at equal distances from the knife edge at equal weights. Let delta be the elevation of the middle point. Now AB represent the arc of a circle. AB represent the arc of a circle. AEB represent the arc of a circle, where E is the middle point of the beam. Now AF is equal to L by 2 and FB is also equal to L by 2. F is the middle point of the beam before bending. So here AFB represent the beam before bending and AEB represent the beam after bending with the elevation of the middle point delta. AEB represent the beam after bending. Now we can see that there is an elevation of the middle point delta. We have to find out the expression for the elevation of the middle point E. How much is the middle point is deflected upwards when the beam undergoes uniform bending. Here R is the radius of curvature. As I specified, the beam is bent into the form of an arc of a circle. Now, the radius of the circle is R. Now, how to find out the elevation of the middle point E in uniform bending? Here, we have to use the condition that at equilibrium, the external bending moment is equal to the internal bending moment. What is the internal bending moment? It is yIg by R. When the beam undergoes uniform bending, after some times an equilibrium is reached. At this equilibrium, the external bending moment balances the internal bending moment. Now, the reaction at each knife edge is W. The reaction at A is W. The reaction at B is also W. Let E be the middle point of the beam. You consider E as the middle point of the beam after bending. Now consider the equilibrium portion EC of the beam. You assume that the beam is now in equilibrium position and you consider the equilibrium portion EC of the beam. What are the forces acting on this section EC of the beam? What are the forces acting on the section EC of the beam? The only external forces acting in this portion are the weight W acting vertically downwards at C, the weight W acting vertically downwards at C, and the reaction W acting vertically upward at the knife edge. And these two forces constitute a couple which bends the beam. That is, in the equilibrium section EC, there are two forces acting. W is acting vertically downwards at C and the reaction is acting vertically upwards at A. And these forces constitute an external couple, and as a result the beam bends into the form of an arc of a circle with a constant radius of curvature. Therefore, this kind of bending is called uniform bending. The beam bends due to this external couple. Now, what is the external bending moment? The external bending moment is given by the external force, that is W, which is acting vertically downwards. W is equal to mg into the distance AC. The external bending moment is W into AC. Since AC is equal to P, we can say the external bending moment is W into P. That is force into the distance from the knife edge. Already we have the internal bending moment, that is equal to yig divided by r. Now at equilibrium, we have taken the equilibrium condition. At equilibrium, the external bending moment balances the internal bending moment yig by r. That is, at equilibrium, Wp is equal to yig divided by r. Therefore, the radius of curvature r is equal to yig divided by Wp. Now, for a given beam, the Young's modulus is constant. If breadth and depth are constant, then geometric moment of inertia is constant. Suppose you are applying a constant weight W, which is at a constant distance P, then we have a constant radius of curvature. That is, in uniform bending, the radius of curvature is a constant. So we can say that the bending is uniform. So we have the expression R is equal to yig divided by Wp. In the present case, we have taken delta as the elevation of the middle point. Delta as the elevation of the middle point. The middle point of the beam before bending is F and after bending is E. So EF represents the elevation of the middle point. Now we can find out the elevation of the middle point using the property of the circle. From the circle drawn on the right hand side, we can write AF into FB, that is equal to EF into FG. This is the property of a circle. What is AF? AF is equal to L by 2. FB is also equal to L by 2. Now what is EF? EF is the elevation of the middle point delta. Now we have to find out FG. What is FG? FG is equal to, FG is actually EG minus EF. EG minus EF. What is EG? EG is the diameter of the circle. Since the radius of the circle is r, the diameter of the circle EG is 2r. So FG is equal to 2r minus, what is EF? EF is delta. Now substitute the value of FG in the RHS of the previous equation. Therefore, we can say the RHS becomes delta into 2r minus delta. That is, L square by 4 is equal to 2r delta minus delta square. What is delta? Delta is the elevation of the middle point. Now in uniform bending, the elevation is very small. the elevation delta is usually very small. Since delta is very small, we can say delta square is negligibly small. Since delta is small, delta square is negligible. So you can neglect delta square from the previous equation. Therefore, L square by 4 becomes 2R delta. Therefore, the radius of curvature R is equal to L square by 8 delta. Now we have two equations corresponding to the radius of curvature. One is yig by wp, other is L square by 8 delta. Since LHS of these two equations are same, RHS should be same. So let us give the proper numbering to these equations. Let the first one be equation 1 and the second is equation 2. Now from 1 and 2, LHS is same. So let us equate the RHS. From equation 1 and 2, we can write yig divided by wp, yig divided by wp, that is equal to L square divided by 8 delta. L square divided by 8 delta. What is our aim? Our aim is to find out the elevation of the middle point E, that is delta. So delta is equal to WP L square divided by 8YIG. Therefore, the elevation of the middle point of the beam, elevation of the middle point E is delta, that is equal to WP L square divided by 8 YIG. Now let us consider two cases. Now for a rectangular bar, we have the geometric moment of inertia is BD cube by 12, where B is the breadth and D is the depth of the bar. Now the elevation of the middle point is WPL square divided by 8YIG. What is IG? IG is BD cube by 12. Therefore delta is equal to WPL square divided by 8y. What is Ig? It is BD cube divided by 12. Therefore, the elevation of the middle point delta is equal to 3WPL square divided by 2y BD cube. This is the elevation of the middle point when a rectangular bar undergoes uniform bending. Now consider a circular rod of radius r. Then the geometric moment of inertia Ig is pi r raised to 4 by 4. Therefore, the elevation of the middle point delta is equal to WPL square divided by 8YIG. Therefore, delta is equal to WP L square divided by 8y. What is Ig? Ig is pi r raised to 4 by 4. Therefore, the elevation delta is WP L square divided by 2y pi r raised to 4. This is the elevation of the middle point when a circular rod undergoes uniform bending.